Okay, so we're talking about derivatives of exponentials. We're going to talk about really two cases here. We're going to talk about the case where we have our function is e raised to a power, so e to the x. And the rule says that when I take the derivative of e to the x, the derivative is itself. So think about that. The rate of change of an exponential is an exponential itself, okay? Let me write down the rule here for a to the x, okay? So this is where we're talking about a is a positive constant, and a is not 0, okay? The derivative of, say, something like 4 to the x or 2 to the x, the derivative of a to the x is going to be defined as rewrite a to the x and then multiply by the natural log of that base, that constant that we have here called a. Okay. In reality, what I have here, these two bullet points, these are actually the same exact rule, because I could have actually written the same thing up here. If you go back and I say take the derivative of e to the x, well, it's going to be let's rewrite e to the x, and then let's multiply by the natural log of the base. What's the base? It's e. Okay, well, you can pull out a calculator. What is natural log of e? Well, that's 1. That's why we don't have to write that. This is e to the x times 1, so we just write down e to the x. Just a little side note here. The natural log of e is equal to 1 because the base of natural log is e. So e to the first gives you back what's called the argument e. So maybe you've called this like a bird method. So think back to log base 2 of 8. You should be able to tell me the answer to that is 3. That's because 2 to the third gives you 8. Okay, so there's that relationship. Your inverse is actually logs and exponentials. I've got that 2 to the third gives me 8. So e to the first is e. So natural log of e is 1. That's why we don't have to write that here. So these rules of logs and understanding those will come up in the next section where we talk about taking the derivative of logarithms. But I want you to realize that these rules are actually the same thing, but because natural log of e is 1, we just write down that the derivative of e to the x is e to the x. So let's see this with a few examples, how to use these rules. So we're just going to ask to differentiate. And part A, just to make sure you were listening, says find the derivative of f of x equals e to the x. Well, you just heard me say the derivative of e to the x is itself. Okay, you don't need anything further. You don't have to write times the natural log of e. You can, but we would still expect you to simplify that. What about if we have f of x defined as 4 to the x? So we have f of x equals 4 to the x. Its derivative then, I just recall the rules. It says rewrite this, 4 to the x, and then multiply by the natural log of the base, which is 4. So there's my derivative. Let's do another example. Let's make it a little bit more complex. So I've got 7e to the x minus 2x to the fourth plus e squared. And so this is where we talk about our sum and difference rules. Remember, those just said you could go through and you could take the derivative of each piece. So essentially I'm saying there's like 3 pieces to this, 3 different functions. Take the derivative of each one, and then you put this back together. So I don't have to do any rewriting. I'm just going to go through and take the derivative. So f prime of x. Okay, well, there's this constant rule. I just learned how to take the derivative of e to the x. The constant's going to stay with it. The derivative of e to the x is e to the x. I've got 7e to the x. I move over here, and the derivative of 2x to the fourth, I multiply that power to the front. So I'm going to have a minus 8x cubed, right? I reduce the power by 1. And then I go over here, and my brain's already been primed to think about e to the x. But e, hopefully you know, is approximately, what, 2.71, I think? It's an irrational number. This is just a number. What's the derivative of a constant? the derivative of 0. So do I have to write that in there? No, but I just want you to not be fooled by that. The derivative of e squared or e to the 1500th, it's going to be 0. So here's my derivative of that function. Okay, now is where we start incorporating some of the other rules that we've learned, like we just learned chain rule. So I'm going to retitle this to say find the derivative, just because these are going to be a little bit different. And I'm going to say part A here is y equals e to the negative 3x. Okay, well, I'm used to seeing e to the x. I know how to take that derivative. But if you think about it, where I used to have e to the x, I replaced the x with another function. I replaced it with negative 3x. That's another function. So what I've given you is an example that's actually a composite function. This is going to be using chain rule. And chain rule says that we're going to take the derivative of the overall function and we're going to multiply by the derivative of that inner function. So in this case, we're going to multiply by the derivative of this exponent. Okay, so I'm going to indicate I'm taking the derivative. So I'm saying y prime. I'm going to take the derivative of the overall function. Well, I'm going to have e to the negative 3x, right? It says the derivative of e to the x was just itself. I'm going to then multiply now by the derivative of the inner function, and that would be actually this exponent part. So what's the derivative of what's up there? The derivative of negative 3x is going to be negative 3. Well, we're not going to leave it like that. We're going to stick that constant in the front. So I've got negative 3 e to the negative 3x. So I've now successfully taken the derivative, and there's the answer. So I had to apply a chain rule. Let's make this a little bit more complex. We're going to use t's, so make sure you write your script t so it doesn't look like a plus sign. And I'm going to have g of t is defined as 10e raised to, and this is all in the exponent, 3t squared minus 2t. Okay, so I've got a constant, this 10. It's just going to go along for the ride is what I say, so it's going to stay multiplied. And I've got a composite function. And so I'm going to take the derivative. That 10 is going to stay there. It's going to multiply by the derivative of the original function, so that means it's going to stay itself, just like we talked about e to the x, the derivative of itself is e to the x. And then I'm going to multiply by the derivative of what's the inner function. Well, what's the inner function in this case, these exponentials, is actually going to be the exponent. And so I've got the derivative of 3t squared is 6t. And then the derivative of negative 2t is minus 2. And notice that's a quantity. So I'm going to get rid of these dots. I'm just putting that in there for sake of explanation right now. So I can move this quantity to the front. I can distribute that 10. So maybe I'll do that here, but I'm still going to be very careful on how I write this so I don't mess up and write something that I don't mean. And so I've got the quantity 60t minus 20 times e raised to, and this is all in the exponent, superscript, 3t squared minus 2t. And that's our derivative. Okay, let's make it more interesting. I'm still taking the derivative. Now I have a constant times an exponential. The base is 4. So I need to think about chain rule because this usually looks like 4 to the x. I also have to think about this constant. It's just going to go along for the ride. So I'm going to take the derivative. I'm going to write it as h prime of x. I'm going to leave that 3 because it's a constant going along for the ride. I think about 4 to the x being that function that's called the outer function, and 5x being what we had called the inner function previously with chain rule. And so chain rule says that I'm going to take the derivative of the overall function, so I'm just going to rewrite that it's going to be 3 times 4 to the 5x. But when I took that derivative when it was 4 to the x, I had to multiply by the natural log of the base. So I've got 3 times 4 to the 5x times the natural log of 4. And then chain rule says I take the derivative of, in this case, this inner function is that exponent. And so the derivative of 5x is just going to be 5. And I just really have to watch out. I mean, natural log of 4 is a number unto itself. I can't multiply the 4 and the 5. I cannot multiply to this base 4 here. And so I just really need to be very careful on how I write this. And so I can multiply the 3 and the 5. That's 15. I can multiply it by that natural log of 4, and you know that really this 4 in your calculator, it comes up with an open parentheses, that's called the argument. I'm just going to put that in there for the sake of how it would look on your calculator, and then that multiplies by 4 raised to the 5x. And so here's our answer. Again, these sets of parentheses are optional, but you should understand that you are not just able to multiply into where that argument is of the natural log. Okay, so I've got another heading. It's still differentiating, but I'm going to distinguish it as part A again, just because now we're going to continue to use these rules, but we kind of amp it up. And so if you have gotten accustomed to looking at these problems in the way that you should start thinking about what rules can I use, and if I can't see them right away, is there something I can do to manipulate it? But I see this as factors, and that means I'm going to use this as for product rule. And so remember, product rule says I'm going to have the first times the derivative of the second plus the second times the derivative of the first function. Okay, so I'm going to take the derivative. I indicate that as g prime of x. I'm going to rewrite the first, which is x to the fourth, and I'm going to multiply by the derivative of the second. We just learned the derivative of e to the x is e to the x. So first times the derivative of the second, plus the second, e to the x, times the derivative of the first. And the first function is x to the fourth, and its derivative is coming pretty quickly to me now, right? It's 4x cubed. And so I guess you could just really clean this up. There's not a whole lot to do to it. You can factor things out. I guess the only thing I would prefer on this one is I move this 4x cubed to the front. But I can do some factoring out some common factors. But that's about it. Let's go on and see how we can involve quotient rule, because we're still practicing all those. So we finished one with product rule. Let's move on to the quotient rule. Example B here. I'm going to make my numerator 3 times e raised to the 2x. My denominator is going to be 1 plus e to the x. If I put this in front of you, I'm hoping you're immediately trying to think of ways, can I make this so I don't have to use quotient rule? Well, no, I can't. I've got actually quantity here in the denominator. So I'm going to use the quotient rule. We've already talked about low d high minus high d low. It's going to be all over low low. And so not rewriting the function, I'm taking the derivative. So I've got y prime here. I could write it as dy dx. So I go low, which is the quantity 1 plus e to the x, d high. Okay, now I have to remember how to take the derivative of this numerator. The derivative of that numerator says that 3 is going to hang out. I'm going to rewrite e to the 2x because this is a composite function. I'm going to multiply by the derivative of the inner function of this, which is 2x. The derivative of 2x is just 2. So I've done low d high minus high, which is 3e to the 2x, d low. So the derivative of 1 is 0. The derivative of e to the x is just going to be e to the x. Okay? And then I go to the bottom and I say low low, so that means I'm squaring the denominator. And from here, it's going to be making sure that I can combine my terms appropriately. So 3 times 2 would give me 6. So I'm just going to make a little note here. And that 6 can distribute. Right? So maybe I'll write it another step, just so I don't confuse myself. Maybe I'll write it like this, 6e to the 2x. So I'm going to rewrite everything. So I've rewritten only the 6e to the 2x with our first part here. I'll distribute in a moment. And then over here, let's go ahead and distribute that as well. So I've got minus and then e to the 2x times e to the x. So e to the 2x, I'm going off to the side, times e to the x. Well, the rule on exponents say that I'm going to keep this base and you add the exponents. So 2x plus x would give me 3x. So that's cleaned up a little bit. And then I've got my denominator squared. And so next what I'm going to do is distribute 6e to the 2x. So 6e to the 2x times 1 is 6e to the 2x. 6e to the 2x times e, do the same thing we did over here. I've got plus 6e to the 2x plus an x would give me 3x. And I'm subtracting 3e to the 3x. This is all over low low, or the denominator squared. And hopefully you're taking a peek at this and you're wanting to combine some like terms to simplify this. Do I have anything that's the same? Absolutely. So I can write this as 6e to the 2x plus 6 minus 3 is going to be 3e to the 3x. And then I could see if I want to go further, maybe see if there's common factors. This is what we've got. Okay, how might we apply these exponential functions? Well, exponentials are very applicable to real world, to business and social science. We talk about exponentials with money, annuities, retirements. We also talk about it when we're thinking about social sciences, when we think about science in general, radioactive growth, radioactive decay, bacteria growth. And so if you have looked at a college algebra book or taken a college algebra course, this problem, the start of this actually is reminiscent of it. It's something we do in college algebra. So this says the quantity in grams of a radioactive substance present after T years is given by this function. It's a formula. You actually could come up with this if you needed to, but they gave it to us. And so it says the quantity is a function of time. How much will be left of this substance is a function of time. And I can look at this, and this actually tells me 100 grams is what we started off with. And I can tell by this, what we call a K value, the rate of growth or decay, that we are actually decaying. This is a negative K, or rate of growth, so negative indicating a decay here. Okay, so it says on part A, estimate the amount, find an estimate of the amount of substance left after 2 years. And so time was given indeed in years, and I know I'm going to find an answer, and it's going to be in grams. Now this gives me the quantity left after a number of years. So for this first part, it should be pretty nice and easy. I'm just plugging in time to be 2 years, and so I will pull out my calculator and I will plug in wherever there's a T, in this case in one spot, the value of 2, representing 2 years. So you pull out your calculator, you find second, you hit where natural log is, you type in this, and let's say we want it to the nearest thousandth. So I would get 43.867, and when I'm talking about real life application, I need to make sure I have my units. This is going to be in grams. This is the amount measured in grams. Okay, I'm going to write down part B here. Okay, part B here is the calculus. It says find the instantaneous rate of change of the amount present after 2 years. Okay, instantaneous rate of change. I'm going to underline that. That should make us realize that we're talking about taking the derivative. Okay, and it specifically says in this case we're going to find it for 2 years. So let's take the derivative of our function. And so I'm going to rewrite our original function that was given. It says that the quantity of the substance present after T years is given by Q of T equals 100 times e to the negative 0.412 T. And I'm supposed to find out how the instantaneous rate of change that this changes after 2 years. So it's going to be a change in the amount over time, right? Change in the amount present, which is measured in grams, per unit of time. So here's my QT, and I'm going to take the derivative, which I denote as Q prime of T. And there's nothing tricky about this one. We're just doing an application of things that we've already done. This is easier than some of the other functions we worked with. And I have an exponential, and I would use chain rule. That 100 is going to hang out for the ride. I'm taking the derivative of the overall function, so the derivative of like e to the t is just itself. So I'm going to rewrite this, e to the negative 0.412 t, but I realized that normally where there's a t, I've replaced it with another function. So now I have to take the derivative of that other function, that function that's sitting up here. So the derivative of negative 0.412 t is in fact negative 0.412. And so I have Q prime of t, so this is going to give me the instantaneous rate of change for any point in time in years here. So I could move that negative 0.412 to the front of that e raised to negative 0.412 t Just going to clean this up a little bit. So this would be what? Negative 41.2. Move that decimal place twice. Good. E to the negative 0.412 t. Now it says specifically find that rate of change when t is 2 years. So I will pull out my calculator. I will type in negative 0.41.2 e to the negative 0.412 times 2. So that's all in the superscript there, that exponent. And if I type that in, I'm going to get a value, and I get a negative 18.14 according to my notes. So I need some units though, and it wants to know the rate of change and the amount after 2 years. So amount is in grams, and that's happening per year. And I guess I should abbreviate since G is abbreviated. So it's negative 18.14 grams per year. So we can see this negative is also telling me that we are decaying, we're losing the amount. Okay? So there we have it. There's our application.